Today's lecture is over all things with exponential functions, equations, and also something called logarithmic functions or equations. First place I'm going to start is showing you what an exponential function looks like. The general form is y or f of x equal to b, which represents the base, raised to some x power. So that's the general form for an exponential function. Now, one of the things you can do with an exponential function is graph it. So we have f of x equal to 3 to the x power. You just draw your xy table and pick a few points to plug in for x. Let's say -1, 0, and a few positive numbers. When you plug in -1 for x, you get 3 to the -1 power, which as a positive exponent, we would flip this. So the opposite of 3 over 1, or reciprocal of 3 over 1, is just 1/3, roughly about 0.33. Next, plug in 0 for x, and any non-zero base to the 0 power is automatically 1. Next, plug in 1 for x. So 3 to the first power is 3. And finally, plug in 2 for x. And that gives us 3 squared, or 9, for the y value there. So let's plot our points. -1 and 0.33 is roughly right there. Got 0, 1. Oops, sorry. 1, 3 is right there. And then 2, 9 is already way up there. So when you connect your dots, your exponential function will form a curve. What if you had a negative exponent? Let's look at one of those. Graph the function f of x equal to 2 to the -x power. You still pick values for x to plug in to find your y values. We can actually use the same numbers. And I'll add an extra number just for accuracy. When we plug in -1 for x, we got 2 raised to the -1. And that's actually 2 to the first power, or just 2. So we can go ahead and plot that point. When x is 0, well, that's still 2 to the 0 power. Actually, that would become, I think, 1/2. Let me see. 2 to the -0 power is the same thing as 2 to the 0 power. So that would still be 1. When we plug in 1, we get 2 to the -1 power, which is the same thing as 1/2, or 0.5. And finally, when we plug in 2 for x, we got 2 to the negative 2 power, which is 1 over 2 squared, or roughly 1/4. So we got enough points. And again, when we connect the dots, our function is a curve going in the opposite direction. Before we talk about how to graph a logarithmic function, I need to show y'all how to convert from exponential to logarithmic and vice versa. So if you have a logarithmic function in the form y equal to log base b of x, and you need to convert it to exponential form, your base is b, your exponent is y, and that's equal to your function x. So let's say we had to graph y equal to log base 2 of x. You could probably graph this immediately on Desmos, but in case Desmos is not available or you're not at a computer, we can convert this easily to exponential form. So our base is 2, our exponent's y, and that's equal to our function x. Now this time around, when we draw our xy table, we need to pick values for y. So I'll just do -1, 0, let's say 1 and 2. When we plug in -1 for y, we get 1/2 for x. So that is going to be roughly right there. I'm off a little bit. When y is 0, we have 2 to the 0 power, which is 1. When we let y equal 1, x is equal to 2. And finally, when y is equal to 2, then x is equal to +4. We still get a curve, but it's going in the opposite direction. Actually, an exponential function and a logarithmic function are inverses of each other. So if you were to draw these side by side, if you had like y equal to the 2x power you needed to graph, then they would be mirror images of each other, the two graphs. The next thing I wanted to go over with y'all, going back to exponential functions, is actually solving an exponential function. For example, we have 2 raised to the 4x power equal to 8 raised to the x minus 5 power. Now, the first step is to try and get both bases to be the same. 8, we can actually rewrite that as 2 to the 3rd power. If your bases are equal, then your exponents are also equal. So we'll bring down the exponents, set them equal to each other. and just solve for x. On the right side, that would be 3x minus 15. And let's subtract 3x from both sides. So our final answer is x equal to negative 15. Let's look at another example of an exponential equation that we got to solve. Let's say we got 25 to the 2x power equal to 125 to the x plus 7th power. Now, both 25 and 125 are base 5 eventually. So 25, we can rewrite that as 5 squared. And 125, we can rewrite that as 5 cubed. And again, because our bases are equal, our exponents are equal also. So we'll bring down our exponents and solve for x. So we have 4x equal to 3x plus 21. Subtract 3x from both sides. And our final answer is x equal to 21. Let's look at one more exponential equation. Let's say we have 1/3 to the x power equal to positive 9. Well, 1/3, we can rewrite that as 3 to the negative 1 power. And 9, we can rewrite that as 3 squared. So when we set our exponents equal to each other, we got negative 1x equal to 2. And our final answer there is negative 2. Let's look at next how to solve a logarithmic, just a basic logarithmic equation. Let's say we have log base 4 of 3x plus 2, and that's equal to 3. And we need to solve for x. Step 1, convert your logarithmic equation into an exponential equation. So our base is 4, our exponent is 3, and that's equal to our function of x. 4 cubed is 64. And at this point, we just have a regular linear equation to solve. So let's subtract 2 from both sides. And we get 3x equal to 62. And the last step, divide both sides by 3. And unless directed otherwise, leave your final answer in fraction form. Let's look at another problem. This one we have log base 2, in parentheses, 7x minus 1, and equal to 5. First step again, convert your logarithmic equation into exponential form. Our base is 2, our exponent's 5. Let me change that 7x into a 3x. And this is equal to our function of x. Now, 2 to the 5th power is 32. And solve your linear equation like normal. So let's add 1 to both sides. That gives us 3x equal to 33. And once we divide both sides by 3, positive 11 is our final answer. While we're discussing logarithmic equations, let's go over some properties of logs. Now there's I guess you would call it a cousin of logarithmic functions called a natural log, and it's abbreviated ln. So the properties I'm about to share with y'all for log is the same thing for natural log. If you have the log of a product, then the way you can expand it out is addition. So log of x plus log of y. And by the way, if there is no base given, it's understood to be base 10, like your calculator is programmed to be. Next up, if you have a quotient, then you can expand that as subtraction. So log of x over y is the same thing as log of x minus log of y. If you have a log of some function, whatever the function is, and it's raised to a power p, then you take that exponent and move it to the front. So log of x to the p power would equal p times log of x. Now, there's one property of natural log that you need to know that's kind of exclusive to that ln, and that is the natural log of e is equal to 1. So let's look at some examples in which we are given just one log function and we have to expand it. So let's start with this one. We have log of 6 times 11, and we can rewrite that as, and let's put a base here. Let's put base 7. So that would be log base 7 of 6 plus log base 7 of 11. Let's look at this problem. We have log base 8. This is a fraction. 7x all over c as in cat. Use the quotient rule first to expand this log out. So that would be log base 8 of 7 times x minus log base 8 of c. We can expand that 7 times x also using the product rule. So the log base 8 of 7 times x will expand out as log base 8 of 7 plus log base 8 of x minus log base 8 of c. Let's use some of these properties. Oh, I got one more to go over with you guys. One more example in which we are given a log and we need to expand it. So this question, we have log base 2 of the cube root of x to the first power, understood to be. Before we can use any of our log functions, we need to rewrite our radical with the rational or fractional exponent. So the cube root of x to the first power is the same thing as x raised to the 1/3 power. Now we can use this last property here, our exponent rule, and move the 1/3 to the front. Our final answer is 1/3 log base 2 of x. Now let's use some of our properties to actually solve logarithmic equations. First one here, we have log base 5 of x plus 3, and then plus log base 5 of x minus 3 equal to 1. Now this is a little different. Our log is already expanded, but we need to condense it into a single log. So we'll use the first property here and rewrite our equation as multiplication. So log base 5 of x plus 3 times x minus 3 equal to positive 1. Now let's multiply our binomials. Oh, before we do that, I'm sorry. Well, we can actually do that in one step if you want. Let's change our log equation into exponential form. So we have 5 to the first power equal to x squared minus 9. And let's add 9 to both sides. That will give us 14 equal to x squared. And you would just take the square root of both sides using the square root property. And we get a plus or minus square root of 14. Let's look at another example, solving a logarithmic equation using one of our properties on the left. We have log base 9 of, and this is a x to start off, minus log base 9 of x plus 2, and that's equal to 2. Look at the properties we have here. We have subtraction, so we need to condense this into a quotient using our second rule. So we'll rewrite our equation as log base 9 of a fraction now, x over x plus 2 equal to 2. Rewrite our log equation into an exponential equation. So that would be 9 squared equal to x over x plus 2. Now we know 9 squared is 81. And you can either cross multiply or multiply both sides by the given denominator. Either way you do it, you get 81 times x plus 2 equal to x. So let's go ahead and solve this linear equation. We got 81x, and I'm just distributing the 81, plus 162 equal to x. And let's subtract 81x from both sides. And that will give us, let me make some more room over here so we can finish solving our equation. (162) equal to negative 80x. And the last step will divide both sides by negative 80. Now, it looks like our fraction can be reduced by a common factor or divisor of 2. So our final answer is negative 81 all over 40. I want to revisit exponential equations and talk about what you would do if you could not get each base to be the same. So let's look at a few. Starting off, we have 7 raised to the 2x power equal to 3. There's no way that 7 or 3 will ever be the same base, but we still need to solve this exponential equation. What you do is, remember that natural log function I introduced to y'all earlier. We're going to take the natural log, or ln, of both sides. Now, on the left side, remember that both log and natural log have the same properties. So we can take that 2x exponent and move it to the front. So we have 2x times natural log of 7 equal to the natural log of 3. Now we're solving for x. We need to get x by itself. So we need to divide both sides by the 2 natural log of 7. We have x by itself. And if my math lab wants an exact answer, then stop here. However, if my math lab wants a decimal answer, then you would just carefully put this in your calculator. And let me see if I can share my calculator. Now, the way I have to enter the natural log may differ from the way you enter it in your calculator, or you can use the calculator that's with your cell phone. Um, Scientific calculator should have a ln or natural log key somewhere. So I have to do mine backwards. 3 natural log, and then divided by, and I need parentheses, 7 natural log times 2. So let me mash equal. And let's say we need to take this out to 4 decimal places. So this will be roughly 0.2823. So my math lab may want you to, from time to time, express your answers in decimal form. Let's look at another example. We have e raised to the x plus 1 power equal to 8. Again, there's no way that e and 8 will ever be the same base. So what you do is take the natural log, or ln, of both sides. Now, the natural log and log, remember, have the same properties. So using the exponent law, move the x plus 1 to the front. So we have x plus 1 times natural log of e equal to natural log of 8. Now, the natural log of e, remember I showed this to you earlier. Natural log of e is actually 1. So all that remains on the left side is x plus 1. Now we need to get x by itself, so subtract 1 from both sides. An exact answer would be natural log of 8 minus 1. Or if my math lab wants your answer in as a decimal, let me put this in my calculator. Natural log of 8 minus 1. And that would be, let's carry it out to 3 decimal places, 1.079. Let's look at one more example where you have to solve an exponential equation using the natural log function. We have natural log of x minus 5. Oh, wait a minute. I'm sorry. Let me erase this part. I'm thinking ahead here. 3 raised to the x minus 5 power equal to 11. Again, 3 and 11, they will never ever be the same base. So to solve this exponential equation, you need to take the natural log of both sides. Now, using the exponent law for natural log, move the x minus 5 to the front times natural log of 3 equal to natural log of 11. Now, to make the calculations a little easier for us, I'm going to, first of all, divide both sides by natural log of 3. And that will leave us with x minus 5 equal to natural log of 11 over natural log of 3. And finally, to solve for x, you would add 5 to both sides. Now, let's say for this equation, my math lab wants an exact answer. So we're finished. Natural log of 11 all over natural log of 3 plus 5 would be your final answer. Next up, I want to go over some application problems with y'all. Give me 1 second and I will find my notes. And we will go over some examples. All right, give me 1 second. Let me copy and paste it to our Paint. Sorry for the delay. Okay, this is a chemistry problem. And let me write the function. It's hard to see here from my copy. Okay, the amount of radioactive material in an ore sample is given by the function I just rewrote, where A of t is the amount present in grams of the sample t months after the initial measurement. Use this function to answer number 7 and number 8. Number 7, how much radioactive material was present at the initial measurement? Even if the hint was not given to you, you know initial means nothing is started, so that's time equal to 0. All right, so everywhere we see a t, we'll plug in 0. All right, and that gives us 100 times 3.2 to the 0 power. And we know any non-negative base to the 0 power is 1. So 100 grams of the sample were present at the initial measurement. Part 2, or number 8. How much to the nearest hundredth power was present 2 months later? All right, with t being 2, everywhere we see a t, we'll plug in 2. All right, let me pull up my calculator. If you have a TI 30X model calculator, then you can plug in everything just like you see it on the screen. Scientific calculator, you kind of have to work backwards. So I'm multiplying the exponent first to get -1. Now let's finish figuring this out. 3.2, and there's my exponent key to the -1 power. And then finally multiply that by 100. And no need to round here because the 5 it is in the hundreds place. So 2 months later, there will be 31.25 grams of our sample left. Let's go over another application problem. And this is one I'm probably sure that you are familiar with. But first, let me introduce or maybe reintroduce our two formulas. So give me just a second to copy and paste both of these. Okay, let me explain both formulas. You use the left formula, and it's hard to read, I'm sorry. That should be A equal to P E raised to the R times T power. Excuse me. You use the left formula if you are investing a certain amount of money and it's being compounded by the bank or your financial institution, it's being compounded continuously. So P represents the principal. A is the final amount that you end up with after T years. And R is your annual rate of interest, initially as a percent, but you would have to convert it to a decimal. So use this formula if your investment is being compounded continuously. Now, if your investment or you may be taking out a loan is compounded other ways besides continuously, then you use this formula. A is equal to P times in parentheses 1 plus R over N raised to the N times T power. All the other letters mean the same thing as in the compounded continuously formula. The N represents how many times per year that your investment or your loan is being compounded. So if it's annually, then your N would be 1 for once a year. If it's semi-annually, then that means twice a year or N equal to 2. Quarterly, that's 4 times a year or N equal to 4. And finally, monthly, that's every month, so that would be N equal to 12 or 12 times. So let me pull up some examples and we will use our formulas to figure this out. And actually, we can do this question. This question will need both formulas. So yeah, let me put this in the middle and erase some of this so we have room to work. Okay, I'll just leave it here. Suppose that $2,000 is invested at 5% interest for 10 years. How much will the investment grow to if it's compounded continuously? And B, find the amount if the interest is compounded annually. All right, for part A, we will use this formula. So let's plug in our given information. The principal is 2,000. R is 5%, but we need to change it to 0.05 as a decimal. And T is 10 years. So let me put this in my calculator. 10 times 0.05. Let's see. You may have to hit your E button first, and then your exponent key, and then do 0.05 times 10 if you have a scientific calculator. All right, and then we'll multiply this amount by 2,000. So rounded to the nearest cent, this will be $3,297.44. Now let's see what we get when we compound if the interest is compounded annually. So since the interest is being compounded another way besides continuously, use the second formula. All right, so let's plug in our given information. P is 2000, R is 0.05. Now, because our interest is now being compounded annually, that means it's just being compounded once a year. So n is 1, and our time is still 10. Now, what I like to do before putting everything into the calculator is simplifying the parentheses as much as possible. 0.05 over 1 is 0.05, plus 1 will give you 1.05 to the 10th power. And let's put that in our calculator. 1.05 to the 10th power first, and then times 2000. That will give us $3,257. And what was the cents? Rounded to 79 cents. So by a slim margin of less than $40, the better option would be to have your interest compounded continuously. This concludes our lecture today on all things with exponential, well, functions and equations involving natural logs, um, logs, and also exponentials.